Hello everyone. In this video, we shall learn about a theorem which basically explicates that if you consider any collection of non-null orthogonal vectors, then that very collection must be linearly independent. So let us now prove this very statement. Here we have considered a collection of vectors, a collection alpha 1, alpha 2, so on alpha n. Each and every member is a vector from the Euclidean space V, and upon which that means upon this vector space, real vector space V, the inner product function is defined by this notation. In a parenthesis by a single comma. This is actually a function. This is inner product function, and with this inner product function, the real vector space V is the Euclidean space. And we have considered this collection of the vectors alpha 1, alpha 2, so on alpha n from this Euclidean space V. And this collection of vectors is an orthogonal collection. That means each and every, this is an orthogonal set of non-null vectors. This collection, that means that this set of vectors alpha 1, alpha 2, so on alpha n is an orthogonal set of non-null vectors, and we shall have to show that this collection of vectors is linearly independent. So let us now start. We are considering this relation. To check the linear dependence or independence, as we know from the theory of vector space, we have to consider such type of relation. C1 alpha 1 plus C2 alpha 2 plus so on plus Cn alpha n, this is equal to theta. Basically theta is the null vector from the vector space V, and each and every this component C1, C2 and so on Cn are the scalars from the field upon which this vector space V is defined. Here we have considered V as a real vector space, so each and every components, this is C1, that is C1, C2 and so on Cn are real numbers. That means C1, C2, so on Cn are real numbers, and we have considered this relation. C1 alpha 1 plus C2 alpha 2 plus so on plus Cn alpha n, this is equal to theta. Theta is the null vector from the vector space V, because we have to check whether this collection alpha 1 alpha 2 so on alpha n, whether this collection alpha 1 alpha 2 so on alpha n is linearly independent or not, whether this collection of vectors is linearly independent or not. To check this we have considered this collection, this relation C1 alpha 1 plus C2 alpha 2 plus so on plus Cn alpha n equal to theta. C1 is a real number, and alpha 1 is a vector from the real vector space V. V is a real vector space. C1 is a real number, and alpha 1 is a vector. Alpha 1 is a vector from the vector space V. So C1 alpha 1, that means the scalar multiple vector to vector C1 alpha 1, this is basically a vector. C1 alpha 1 is a vector, and similarly C2 alpha 2 is a vector, and so on Cn alpha n, this is also a vector. So C1 alpha 1 plus C2 alpha 2 plus so on plus Cn alpha n, that means this left hand side portion C1 alpha 1 plus C2 alpha 2 plus so on plus Cn alpha n, this is actually a vector. This is basically a vector. We are considering this vector as a first component vector, and we are considering these vectors c1 alpha 1 plus c2 alpha 2 plus so on plus cn alpha n as the first component vector and alpha I as the second component vector of these ordered pair. Here we have so considered. I means the index number which varies from 1 to n. That means we are considering this inner product c1 alpha 1 plus c2 alpha 2 plus so on cn alpha n comma alpha I, where alpha I is a member from this collection, where alpha is a member from this collection of vectors alpha 1 alpha 2 so on alpha n. That means we are considering this inner product, basically for each and every member from this collection alpha 1 alpha 2 so on alpha n. So we have written notationally here I varies from 1 to n. That means we have to calculate this for I equal to 1, that means for alpha 1, similarly for I equal to 2, that means for I equal to 2, and so on for alpha n. And as the right hand side portion of this algebraic identity is theta, and as we are considering the inner product of this left hand portion, left hand side portion c1 alpha 1 plus c2 alpha 2 plus so on cn alpha n with the vector alpha I, so we have also considered the right hand member theta. We have also considered this inner product with the right hand member theta, that is as theta comma alpha I. This relation from this equality we have written this line. And we all know that the null vector theta is orthogonal to any other vector, null vector or non-null vector. The null vector theta is orthogonal to any other vector, so this inner product value will be equal to 0. That means theta comma alpha is equal to 0. We have written here that this is equal to 0, right hand member equal to 0. And try to remember the linearity property of inner product function. What was the linearity property? Try to remember that very. And according to linearity property, we are writing this left hand side portion in this form, in this expanded form. That means this first component is c1 alpha 1 and this is alpha I. So if we expand this, we can write this c1 alpha 1 comma alpha I as the first member, c1 alpha 1 comma alpha I as the first member. Similarly, this is the second component c2 alpha 2. We are considering this c2 alpha 2 and with this alpha I. We can write c2 alpha 2 comma alpha I. Similarly, we shall do it for each and every component. And similarly for this component cn alpha n and alpha I, we have written here cn alpha n comma alpha I. Obviously, alpha I being a member from this collection of vectors alpha 1, alpha 2, so on, comma alpha n, in this linear combination c1 alpha 1 plus c2 alpha 2 plus so on cn alpha n, there will be a middle portion where the term ci alpha I here will be present, and in that very case for this component ci alpha I and alpha I, we can write in some middle portion this value, this inner product value Ci alpha I, comma alpha I. So we can write this left hand side. We can write this left hand side as C1 alpha 1 comma alpha I plus C2 alpha 2 comma alpha I plus so on. In a middle portion Ci alpha I comma alpha I, each and every this order pair is basically a inner product value, and plus so on Cn alpha n comma alpha I, Cn alpha n comma alpha I, where the right hand member is equal to 0. From here the right hand member is equal to 0. We have written here. Now try to remember what was basically the homogeneity property of inner product. In homogeneity property we have learned such type of scalar multiple vector, if there be present in any ordered pair of vectors as one component, we can take that very scalar outside the parenthesis. So from here C1 alpha 1 comma alpha I, what we can write? We can write this is C1 into alpha 1 comma alpha I. And we have done similar thing for each and every member. And we have written for this second component C2 alpha 2 comma alpha I, this C2 into alpha 2 comma alpha I plus so on. For this member Ci alpha I comma alpha I, we have written Ci into alpha I comma alpha I, and so on. For this last member Cn alpha n comma alpha I, for this last member Cn alpha n comma alpha I, we have written Cn into alpha n comma alpha I. This is equal to 0, the right hand member. Now here try to recapitulate what was the definition of orthogonal vectors. Orthogonal set of vectors. We have learned that two vectors are orthogonal only when if we consider the inner product of those two vectors, considering them as a component of the ordered pair, and if the inner product value is equal to 0, then that two vectors will be called orthogonal. Here we have considered a collection of vectors alpha 1, alpha 2, so on alpha n, and for this very collection, when this very collection will be termed as orthogonal collection, if we consider if any ordered pair of vectors forming from this collection of vectors whose two components are distinct, and if whose two components are distinct, and the inner product value of that very ordered pair is equal to 0. So this collection being an orthogonal collection, if we consider any ordered pair of vectors, that means alpha I comma alpha j from this very collection where I not equal to j, then the inner product value of that very ordered pair must be equal to 0. So from here alpha 1 comma alpha I, the inner product value of this ordered pair alpha 1 comma alpha I, this must be equal to 0 because here alpha 1 and alpha I are not equal. Similarly, the ordered pair alpha 2 comma alpha is also equal to 0. The only term alpha I comma alpha I, this will be remained non-zero. Why? Because in case of the two components same ordered pair, nothing there has been mentioned in the definition of orthogonal collection of vectors, orthogonal set of vectors. And we also know that for each and every non-null vector, if we consider the same vector as the component of an ordered pair, then the inner product value must be positive. So this is alpha I comma alpha I is basically a positive real number here. And so on the last term, this is also alpha n and alpha I. So this ordered pair alpha n comma alpha I must be equal to 0. So from this line we can write Ci into alpha I comma alpha I. This is equal to 0, and as we have already stated that this alpha I comma alpha I is a positive real number, the remaining portion Ci must be equal to 0. So this implies Ci equal to 0. And Ci equal to 0, I here represents as the general term. And we are calculating this Ci for each and every I. That means for I equal to 1, for I equal to 2, so on for I equal to n. So what can we say from here? That each and every member, each and every scalar C1, C2, so on Cn, all are equal to 0. So according to the definition of linear independence of a set of vectors, and also from this present discussion, we can say immediately that this collection of vectors alpha 1, alpha 2, so on alpha n is linearly independent. Similarly, if we consider this collection alpha 1, alpha 2, so on alpha n, if we consider this collection of vectors alpha 1, alpha 2, so on alpha n as an orthonormal collection of vectors, we can also prove similarly Ci equal to 0 for I equal to 1 to so on n, and the similar arguments will hold good. Only in place of this alpha I comma alpha I, we have to replace 1, because this is an orthonormal collection of vectors, and this being the same component, the value of this alpha I comma alpha I will be equal to 1. And similarly we can say that if this collection is an orthonormal collection, then this collection must be linearly independent. Okay, thank you.